Hi, everyone. I'm Antonio Torralba, so I'm going to talk about some of the research that we are doing in my group. And so I focus on computer vision, and as you know, machine learning and computer vision in general, one of the reasons why it has made so much progress in the last decade is because of access to large amounts of training data. This visualization here shows the type of data sets that people are using in computer vision to train vision systems, and is plotted as a function of the amount of data available. So the horizontal axis is time, vertical axis is number of images in logarithmic units. So this is an exponential growth as you move from one year to the next, and these data sets have been becoming larger and larger and larger. One of the big challenges is that these data sets need to be annotated. You need to have labels for all of the different things that you are interested in building your system to be able to solve. And this is just general across machine learning. One of the big bottlenecks when you start building a company or you try to solve a particular task is what data are you going to use to train your system and all the issues that come with that data. So this is a very important problem, and it's actually one of the sources of expense that you need to, investment that you need to put into creating this initial seed to build your application, but also in research is generally an important bottleneck in order to move forward. And generally, you have these two objects that you care about, the input data, the observations that you will make about the world. In computer vision, that will be images, but this could be computational biology or any other field. And then the labels, the outputs that you want to be able to generate, and you want your system to be trained to solve this particular task of associating the input data with the output that you want to have. In the last few years, the community, well, for a long time, the community has been focusing very heavily on trying to get rid of the labels. How can you build a system that learns in an unsupervised way to build some representation that is going to be useful to solve your task? And in the last few years, there have been pretty good advances on solving this task to the point that now it's possible to build representations that are pretty competitive with respect to a fully trained system. So, the question is, do you really need labels in order to be able to learn to see? And we know that humans don't need labels. No? Humans learn by themselves most of the time without the parents, teaching you what the meaning of every single pixel, that every single light ray that hits your retina, what it means. Just by playing with the world and interacting with it, you build representations that seem to be very powerful at the end in order to solve the task, and then humans come, your parents will come and just teach you the association with a few words, and kids learn really, really quickly. So we know that it's possible to some degree to solve this problem. And there has been a lot of research in computer vision and across machine learning in order to create these type of systems that are able to learn by themselves. So the way that they do it is by creating some pretext task that is not the one that you want to solve, but it's some task that you don't need data actually to solve it, but you hope that if your system solves that task, it will be able to learn some interesting representation. For instance, you could train a system to take an image that is, you have a normal image that is a color image, and then you remove the color, and you teach the system to predict what the color should be. So giving just the black and white picture, what the color should be. And that's a way, it's a way of training a system that doesn't require any kind of training data labels. The labels are already part of your data. You also know probably about generative models where you teach a system to render images that look realistic. And that's another way of training a system with no labels whatsoever. And it's training to solve a very complicated task. In this case, to draw images that look real. And in order to do that, the system must be building some really interesting representation inside. So that's another way. And then another set of techniques that has been also very popular is just to think of learning a representation as in the framework of something that is called representation learning. And basically, when you have a system, let's say that you want to build a computer vision system that does image tagging. So in this case, the input will be one image, and you just want to output one label that will classify that image as being, well, a picture of a dog, or a purse, or an iron, or a lamp. And you just have this multi-class problem that you want to train. And you can think that a neural network, which is the standard machinery that is currently used, It's just a transformation between that input image and some representation that is going to be useful to solve your task. And then at the end, the only thing that you have is a way of translating that representation, that is something that the neural network builds inside, translate that representation into the final labels that you want. So here in blue is indicated that representation, and then there is a simple linear transformation in general, something very, very simple that will transform that representation into the labels that you care about. So how do you train that if you don't have labels? So you have labels, then the weights of the neural network are trained by just minimizing your error rate. But if you don't have labels, what do you do? So one thing that people have proposed, and it works remarkably well, is to do the following thing, which is called contrastive learning. You take a set of images that have no labels whatsoever, and you want to build a representation that will solve the following task. Let's say that you have a picture of a dog, and you will define, because you don't have a class, you don't know that this is a dog, you will say, well, I'm going to put a label to this image. And you can consider that now every single image is a class on its own. And you will train a system that will put that image as far away from all of other images. You want to make all of the images different from all of the others. But you also want to create something that also attracts things, because otherwise you will just try to make your representation to be very, very large, and that will put images very far away, but it's really not solving anything. So another thing that you can do now is you take that picture and you create other versions of that image by cropping it or changing the colors. You know that that's not changing the label, but it's changing the visual appearance of that picture. And now what you want is that the same representation should put all of these different versions of that image nearby. So now you have these two forces. You want to have things that are nearby, that are of the same picture, all of them close together, and things that are different from other images far away. And this surprisingly works remarkably well. So this is a very simple technique, and just by seeing the technique, it will be hard to guess, okay, it sounds fine, but how could this do better than having labels? But people have proposed a number of sophistications of this particular approach, and it works really, really well. So we know that we can get rid of labels. But images also put a number of challenges. In some domains, capturing data is even difficult. The observation data itself might be quite hard to get. In the case of images, you can have all kinds of issues. You can have privacy constraints, copyrights. There might be a number of things that prevent you from actually having images. And there might be also other domains like computational biology and so on, where collecting the data itself might be quite difficult. So the challenge that we wanted to solve is, well, do we really need images? Can we get rid of the images themselves too? So we just want to get rid of all of the data. So how do you learn to see if you have nothing? You have no labels and you have no images. So now what I'll talk about in the rest of the presentation is how do we solve this problem and how far can you go? So here is the task that we'll try to solve. It's a 100 classification task where there are 100 classes. Here there is just one exemplar per each class. And I want to train a visual representation that, given a picture, is able to tell me which of these classes it belongs to. So this will be my test set. But I'm not going to use this for training. I'm going to train the system with no images whatsoever. So if we come back to this problem, where we have a neural network, the training is about getting the weights. I want to know what are the parameters that define this neural network. So how can I get those weights if I have no training data? OK, so this is the plot that I'm going to be showing over the presentation, just to show how we climb the performance game in order to build things that work better and better and better with no images whatsoever. So here what I'm going to show is the vertical axis is going to be performance at this task of classifying objects across one of these 100 classes. And the horizontal axis is going to be different models that I use to train my system. So because there are 100 classes, if you just do it by chance, you will have a 1% performance. So it will be very, very low. One thing that you can do, of course, is to train with images. You can actually use real images and train your system and see how well it does. And at this task, it does around 54%. So now the question is, how far can we go if we have no images? So this is just contrastive learning using real images. So what can we do if we have no images and no labels? We have nothing. So one thing that you can do is just put random weights. What happens if you just take the network and just put random weights, and that's it? That's your visual representation. How well will that work? That's a way of training the network with no images and no data whatsoever. So maybe it does already something. So if you do that, it's actually better than chance already. It does around 20% classification rate, which is quite surprising, and it's because these neural networks capture very well, very nicely, some of the properties that define natural images. So the structure of the network already contains enough information that is capable of solving, at some primitive way, this task, even when it had no data. But can we do better than this? Well, another thing that you could imagine, and this is also another technique that is quite popular, is just to simulate your data. You can simulate visual data. You can have computer graphics that render environments that look like real, and just train your model with that. So this is an approach that a lot of groups are taking, and is very popular in a number of domains. Just train something that will learn to simulate your data. And in fact, if you do that, depending on how good is your renderer, you can do much better or worse. So here there are just two different synthetic worlds that are used to train this model to learn some visual representation, and how well it does at this task of classifying one image as belonging to one of these 100 classes. So one of the data sets does slightly better than the random weights. These images look very different from the type of images that we will use later. And then the other data set, which is just images that come from the game Minecraft, it actually performs fairly well. It's around 40% recognition rate. But that still has a lot of knowledge about the visual world. It has, you have to create content. These simulators are actually expensive to build. And depending on the area where you are working, building the simulators will also be a very expensive experience. It will be a big investment. So what happens if you don't want to use real images, but also you don't want to use computer graphics? What else? What else can you do? Well, we know that, oops, it's stuck. Surprise, what will happen now? So while they are solving it, OK, here it is. OK, we know that biological systems seem to learn something about the visual world even before they open their eyes for the first time. So here, what you see are snapshots from the mice, from a mice before being born, where they recorded activity on the retina. And what you can see here is that so what you see here are pictures of the image that is created on the retina, and it seems that there is some kind of spontaneous activation pattern that happens on the retina, creating something that is called retinal waves. And this has been known for a while. This is just one recording done recently, but this is a phenomenon that has been known for a while. And one of the beliefs is that these patterns is not noise. It's not just something that happens accidentally. It has a purpose. And that purpose could be that these retinal waves, which are these patterns that actually move over the retina, start training the visual system to do motion detection. So even before the animal has opened the eyes, it already knows how to detect motion. So can we exploit this idea to train visual systems? Oh, now it moves the movie. So this is the recording of the movie. So can we actually learn by just looking at different noise patterns? And that has been one of the lines of work that we had in my group. So people have shown, actually, that if you create images that are synthetic, but are just fractals, so these are very simple generative models that don't require the same type of labor-intensive work that will require to build a virtual world as a simulation, if you use these images and you use them to train a representation by using these representation learning techniques that I described at the beginning, you actually build representations that are pretty good. And in fact, they perform better than one of the virtual worlds that I was using, not as good as the second one, as Minecraft, but pretty surprising performance, given the fact that these images are just fractals on a black background, and they don't look like anything like real. So what else can we do? Can we just train a system by looking at images that look like this? This is noise, no? Like if you had your TV, an old TV that is not tuned to any particular channel, can you actually learn to see by looking at things that look like this? Of course, the answer, no. How could you learn anything by looking at something like this? No, there is nothing. But maybe we can be a little bit clever about how we generate that noise. So for instance, what I'm showing you here is noise that we are creating that starts to mimic some properties of natural images so that we can use them to train. So the game here now is I'm showing you three images that are real, 3 images that are fake, that are just noise, it's just noise, and these are just crops from images, and your task is to tell me which ones are real and which ones are fake. So you don't have to say anything, but just think a little bit about it. OK, so this is the answer. So maybe some of them you could guess, but they start looking pretty similar, no? So these are just noise processes that that are designed in a way that they capture properties of the real world. So what type of noise process can we use? Well, in the 90s, there was a particular image model that was very popular, and it was called the dead leaves model. And this is something that was introduced in the 60s, but it became very popular in the 90s as a model of what a natural image might be, when people were trying to study how to perform basic computer vision algorithms and also for things like TV coding. And these images are just formed by a set of squares that are placed randomly on the image. So you can think of leaves falling on the ground. In this case, the leaves happen to be squares, and they have different sizes. And as they fall on the ground, they start occluding each other. Very simple images, very simple to generate. And here there is a sample of many images processed by that process. But once you have this, which is a very simple line of very simple script, you can generate millions of those. So what happens if you train a model to learn to see by looking at these things? And by the way, you can make them more complicated. You can have the squares of having different orientations. You can have different shapes. It doesn't need to be just squares. It could be triangles and circles, just simple geometric figures. So if you use them to train, this is what you get. There are the bars marked in green there. So in particular, the 3 that I'm showing there are different dead leaves models with different complexities of the shapes. And the one that is performing the best is the one that had all kinds of different shapes. But you can see that it's getting really close to the performance that is achieved by Minecraft. And this requires no team of engineers programming a complex virtual world. It's just a set of squares and geometric figures on top of each other. Very simple set of images. What else can we do? There is another remarkable property of natural images. So, if you take an image and you compute the Fourier transform, for those of you that might remember what the Fourier transform is from some of the classes that you took, maybe, one remarkable property is that they have always the same shape. What this means is that if you look at an image, the coarse elements have a lot of energy, and the details in the image have always very small energy. And this is something that happens for all natural images. And it's not something that happens with absolutely random noise. It doesn't have this property. It's very hard to find an image that if you take a picture and you compute the Fourier transform, it doesn't look like that. So you can use that property now to generate noise that captures that property. And just to show you an example of that even your visual system is tuned to that. If you look at this, you might see a wave that is going from very slow frequency, varying very slowly, to something that varies very fast. And if I ask you, to look along the vertical axis and indicate when is that you stop seeing that wave, so here the wave is just decreasing in magnitude, if I ask you to trace a line across the screen, probably you will do something like this, more or less. But in fact, the amplitude is always the same. There is no difference across frequency. The only reason why you see the low frequencies vanishing earlier is because your visual system is trained also to deal with this 1/f, this particular shape of the Fourier transform in natural images, and is compensating for it. So you are very insensitive to low frequencies, very sensitive to mid-range frequencies, and then, of course, at the end, the details start vanishing. So these are images of noise generated to have that property. Again, they don't look like real images at all, but they have some of these properties that natural images like so much. Also, colors are very important. Colors in natural images are distributed generally across uniform patches and so on, so we can also incorporate some of that information. And then you get images that look like this, where there are colors distributed along patches, and it has this property of concentrating energy in low frequencies. So if you train that, then you get this bar here. You get this performance that is actually pretty close to the deadlifts models, but it's slightly, it's in the middle. It's a process that is also very easy to generate, by the way. It's just as hard as the deadlifts model. It's just a few lines of code. Another remarkable property of natural images, if you take an image and you compute the difference, well, if you compute the histogram, generally you get something like this. This is how many pixels of a particular intensity there are in this picture. And you see this distribution that doesn't seem to have any particular shape. And a different image just shows you something completely different. But if you take the image and you compute differences between nearby pixels, then you get this particular image. Here, it looks like using the emboss property filter in Photoshop. Basically, what it's doing is just computing the difference between one pixel and the pixel that it has to its left. And that's what you see here. Gray means that there is no difference. That's the 0. So when you do this to natural images, it doesn't matter what natural image is. If you look at the histogram of values, then you get something that looks like this. And it always has this shape. You can see how well organized this particular histogram is. It looks very different from the one on the left. And if you do it for vertical pixels, you get the same thing. And if you do this for any image, you always get these very fancy distributions that always look alike. So here there is noise processes that also have that property. And if you train those, then it gets even better than deadlifts models, and it's also almost matching Minecraft performance. But we can do even better. So we know that generative models like GANs and so on, they are really good at rendering images. When you're trained with real images, like this is a particular GAN model, you get images that look very, very realistic. And this is because these structures, these architectures already contain a lot of useful information about what is expected on a natural image. They contain the right structural priors. And people have worked very hard to make those priors to be inside the network. So what happens if you take one of these GANs, one of these generator models, we cannot use images, so you cannot train it with real images. But instead, you just put random noise in the weights. Just put random weights to it. Or maybe weights with special initializations, and we have explored a number of them, but without using any real image to train it. What happens if you sample from it? Well, you get images that look like this. They look like some of the images that I was showing before, but now even they seem to have some 3D to it. There seems to be like shading effects, and these properties are also very important in natural images. And when you use them to train, you actually get the best performances. And these models are, again, very easy to use. And it requires no real images whatsoever. And you can see that now the gap with training with real images is getting pretty small. And then lately, what we have been doing is also explore what happens if you train with processes that are created to generate interesting geometric figures. And this is a piece of code that is used to render images with OpenGL. This is called a shader. So the full code is just that piece that you can see there. And when you run it, it generates the images that you see on the bottom. And there is a big community of people working in creating these very interesting shaders that render images that are just interesting to look at. So we collected 20,000 of those. And each time that you run them, you have a diverse set of images that come from each of those. So now what happens if you use them and you train a system that learns to see by just looking at these rendered images from these shaders? This is the performance that you get. So it got really, really close. It's getting really, really close to the performance that you get with actual real images. And our belief is that this small gap that is remaining here, we can close it eventually. There might be some process out there that is not real, it doesn't require the effort of creating a full environment that looks photorealistic, or a full simulator of genetic data, or whatever type of data that you need to work with. There is some simulator there that captures some of the important characteristics of that will train a model that will get you 90% the way to what you need to have. So this is kind of the agenda that we have, building these processes that learn each time better and better in order to train systems that can see. But in general, we want to explore this in other areas too. but that require not input data. There is no need to collect any data whatsoever. It's just about thinking about what are the physical properties that define your problem and build systems that generate noise that captures those properties. So what I think is going to happen is, there has been this trend of building systems that learn with more and more data, and what I hope is that eventually this is going to go down, and now there will be a new trend about trying to create systems that learn with each time less and less data. And I don't mean here unlabeled data. I mean no data whatsoever. There is no data whatsoever in training this system. So thank you so much for your attention. So this is the collaborators working on this project. Manel, Jonas, Tongsu, Felipe Sola, another professor at MIT, and myself. Thank you so much. OK, so I guess I should read the questions. So how might this map to other types of applications, such as language, signal processing, business data? So I think that this is a very important area of research where, as you start focusing on specific applications, where the task is even better defined than just building these generic visual systems, it will be possible to define these processes, these noise processes that will be very effective. I think that, for instance, in natural language, people have shown already that even when you train natural language systems with random text that you just generate randomly by sampling letters, these models are already pretty good at building some initial knowledge about what language structure might be, and then you can fine-tune with real language, and they learn much faster. I think that in other domains, particularly, for instance, in healthcare, where you might have data that has very, very strong structure, these techniques might be even more powerful than the ones that I have been showing just for generic vision. So I think that this is a very interesting area of research, but I think that it will, it shows a lot of promise, and I think it's going to change, or has the potential to change, how you initiate research or building products in specific areas where data is just hard to get. OK. Yeah, so I didn't went a lot into the detail on how performance is defined here. So let me explain then a little bit better how we evaluate performance here. So the goal of these noise processes is to train a visual representation that is useful to solve tasks. At the end, you need to solve your particular task. So there are a number of ways in which you can do this. So we use these noise processes to train the visual representation, but the visual representation still is not the labels that you need. It's not one of those 100 classes. So what you do at the end is you need to have some training data to learn just the last layer, that is the final classification task that translates your visual representation into the labels. And that's the way that we measure performance. We don't allow anything else to change in the network, just the final translation. Another thing that you can do in order to evaluate performance that we don't require even having this is we can use it as a nearest neighbor. So just use the representation as a way of telling when two images are similar or not. And then if you do that, then you can have a test set where you are just using your representation to tell, given one image, which other images in that test set are equal or similar or belong to the same class or not. And then you can count how many times that system is right. In that case, there is no training whatsoever into the system. OK, so the next question is really related to interpretability. What is that deep models are actually doing? I think there are a lot of ways of answering this question. So there is another very important line of work in general in the community about trying to build systems that explain themselves or building techniques that allow to interpret what is that a deep model is actually doing when has learned to solve a particular task. So in my group, we have been working a lot in something that we call network dissection, which is given a system that is already trained, can you act like if you were a neuroscientist, go into the system and try to identify what every single unit inside that system is doing? So that's a way of trying to get a hint about what is that these deep models are actually doing inside. And really what they are doing is, to some degree, they are learning to capture some of the concepts that are relevant to solve your task. And some of the internal representations are actually quite sophisticated. These models are capable of identifying elements in the image or in your data that correspond to meaningful concepts. And it's using them in a way that in some cases, it kind of looks like what it seems to be like the reasonable thing to do. So it depends on the task, whether you can actually interpret or not what these models are doing. But this is a very active area of work, trying to understand what these models are actually doing, not how they work, but what is that they do once they have been trained, how is that they solve the task. OK, well, thank you so much.